Everyone hear me okay? Cool. I'm going to start with a story that's not on the slide, completely separate, picking up on what Sean was just talking about there, because I thought that was a really cool talk. So I'm a lecturer at a university in the UK, and thank you for not starting the clock, because this isn't part of my presentation, just a random story. So a couple of years ago, I had an undergrad student who was a firefighter, and he was interested in this topic of shoulder widths. So he found that a lot of the original research came from the French army and all these kind of things about widths of shoulders, and he thought, well, I think because he's very British, he thought, I'm going to have a go at this myself. So he started measuring students before and after lectures. Not necessarily the same students, he was just doing it in between my lectures. He was one of my students, it was a good data set. And he accidentally measured the same student twice, before the lecture and after the lecture, and found that student had grown by 2 inches in the shoulder. True story. So I said, what happened? Why was he so pumped up after the lecture? Like, what was going on? He was like, really? And it turned out, actually, it was quite an interesting kind of biomechanics thing. So the first time he measured him, he didn't tell him why. So this student was kind of slumped over and he was kind of, whatever. And afterwards, he told him what he was doing. So the student, of course, straightened his back and said, oh, very good, I'm going to be the widest person in the room. And his dissertation changed subject immediately because he suddenly became interested in, if we're charging around in an airport, are we slumped down, looking at the ground, not really care what we're doing, jet lagged, or are we actually, everyone get out of my way, I'm going to make myself as big as possible? And it became quite an interesting thing. He never solved it. There's no answer to this story. It was just an interesting point about how you would measure somebody's shoulder width, and actually you can give it that, or you can kind of change it completely. So yeah, cool talk. We'll pick up on it later if that's all right. Anyway, we can start the clock now, chaps. Thank you. Good afternoon, everyone. It's me again, I'm afraid. Thank you to everyone that was here yesterday and for picking up on yesterday's talk. I have a totally different talk today. It's far less technical. Duck, as I say that. Somebody launches a glass at me. It's a case study, this one. Slightly different from the same research group. Research that I've been working on. I've got the same team as well. So we've got Chris, we've got Jack, Renee, Joel, Kirsty, who's at the back of the room, myself. And we're looking at some rationalization of CFD geometries. For anyone that wasn't in yesterday, my name is Joe Hart. I'm the founder and CEO of the Delta Innovation Group. I'm based out of Preston in the north of England. We have our own lab that we built and opened in January called the FRC, Fire Research Centre. It's where we base our business and do all of our work from. I spend most of the time in London working commercially, and I teach as well. I kind of travel around a lot, but as I said yesterday, I'm very much a working CEO, so I'm very much kind of at the coal face of the technical stuff, like in this presentation here. So for anyone that was here yesterday, I said that what I like to do at the start of all my talks is to convince you why you should care about the next 13 minutes, 45 seconds. This study, I'm going to skip over this one and come to this slide, is really intrinsically related to this fire, the Grenfell Tower fire. Now, I'm sure we're all aware of this one. Certainly if I was doing this talk in London, everybody would know. Loads of people I speak to were there. I was there the night that the Grenfell Tower fire happened. I lived in London. I went down to the fire, saw it firsthand. Our industry changed overnight, certainly in the UK, practicing as an engineer in London. It was a huge seminal event for us. 2 weeks ago, we got the final inquiry report. Our industry changed again overnight 2 weeks ago. The reason that we're so interested in residential fire safety and residential modelling, which is what my talk is about today, harks to this incident, and this highlights some of the issues that can go wrong when things are designed incorrectly. The Grenfell Tower fire, the Grenfell Tower itself was constructed back in the 1970s. It was overclad in the early 2010s. It was overclad with a combustible material. I'm sure that this narrative is familiar to us all. On the 14th of June, 2017, a little over 7 years ago, a fire happened in a refrigerator in flat 16, which broke the window, melted the UPVC, spread to the external cladding, and engulfed the building. 72 fatalities, 71 of which were on the night, 1 was later, and over 100 injuries. The estimated cost that's been released recently to the UK economy is upwards of 50 billion, with a B, 50 billion pounds. The UK government themselves have released 5 billion pounds to reclad buildings similar to Grenfell across the UK, and that's a huge package of works at the moment that we're seeing in our industry. So as I say, I always try to sharpen the mind a little bit to see why we care about this subject. I've got a little bit here. I added a couple of slides last night, actually, based on some discussions last night that I had with some of you guys. I'm acutely aware I'm not in the UK anymore. I'm very much in Kansas. And some of this is not known. So a really quick highlight and run through of how this works for us in the UK, our building regulations. It's one slide, I'll do it in 10 seconds. Our requirements are completely functional, which means we are told what we have to do, but not how to do it. So our functional requirement for fire safety in the UK, all buildings in England and Wales, and Scotland in fact, consists of 5 things. We have 5 requirements for fire safety. They're called B1 through B5. B1 is means of warning and escape, B2 is linings, B3 is the structure, B4 is external fire spread, and B5 is access and facilities for the fire service. And what that requirement actually consists of is what's on screen there. That's our entire legal standing in the UK for fire safety for means of escape. It's one sentence. We design buildings around that one sentence. If we are prosecuted for breaching it, we are prosecuted for being in breach of that one sentence. And the words I always highlight in there are the word appropriate. Appropriate is not defined in the UK regulations. Appropriate is not defined in any guidance, really. It's up to us as designers to define that ourselves. And when we are doing that, again, this is a very, very quick kind of summary before I get into some of the bits we've looked at for this piece of work. We broadly have 3 approaches to doing this. We have codes and standards as we'd have anywhere in the world. We call that our approved document B is our standard prescriptive guidance approach. And we can design buildings to meet that guidance. It's inferred that if we follow that guidance, we are therefore satisfying our legal duties under the building regs, and we can follow that established code of practice. Alternatively to that, the job of an engineer, which is what I consider myself to be, is to do performance-based design. First principles, what we're all talking about here in our presentations and in the bar afterwards. Performance-based design, true kind of engineering from first principles. And the other type of analysis, the other type of design that we may undertake is comparative analysis. We do a benchmarking exercise. If this is the level of safety that would be accepted under prescriptive guidance, and we can demonstrate that we are equivalent to, we are as safe or safer than that guidance, we've carried out an engineering judgment and we've said that, therefore, this meets our legal duty, our statutory duty. So far, so straightforward, I think. And I'm going to hone in on that comparative analysis for the rest of this talk. So, approved document B looks like this. This is what it would tell us for design of a single stair building, in this case. The image down at the bottom there, I'm going to try to do a Rishon here. How did you do the thing where you get the click? Look at that. No one told me this yesterday. I was waving my arms around yesterday. I watched the video back. I look like a right muppet. Anyway, I found a button. There we are. That one there, okay? Standard single stair resi design that we would have up and down the UK. It's exactly what Grenfell was designed to be. In actual fact, the image in our guidance looks distinctly like Grenfell Tower. 4 flats around a central lobby serving a single stair. And our design that we would look for is to ventilate that corridor. So anything that's in grey in our guidance, we would ventilate. And we have a standard approach for this under our guidance, which is to have a natural shaft opening, 1.5 metres squared. We ventilate via that. That's interfaced with the fire alarm system. If we get smoke in the lobby, that opens and it ventilates naturally. There's no fan, there's nothing else, it's just a vent. Traditionally, came about when we had PPV, positive pressure ventilation for the fire service. They would come in with a fan set that they'd place and you can ventilate that way. There are only 2 fire services in the UK that use PPV anymore, but we still design buildings like this, and we may, I hope that carries on for the whole talk, and we may in fact put a mechanical system in, which is what we're going to come on to here. So, mechanical smoke control shafts, big part of our work, certainly that I use with my consultancy side of the business. One thing I didn't touch on that I wanted to at the beginning is about our research work. So the research that we do in my organisation is slightly unique. So within my team I have a research group, I have a various research assistants, all my engineers do research alongside their consultancy work. We are largely self-funded. If the SFP would like to give us some money, you are more than welcome. But we do broadly self-fund all of our research, which means a lot of it is related to our consultancy work. I press into my guys massively. What we're interested in is what we call solutions-based research. When they put a bid into us for internal funding, the first question I ask them is, do we care about the answer? It's not just a piece of research that's kicking something along. It's not something that doesn't take us anywhere. What's the answer going to be? Do we care about it? Are we going to use it? And that's how we got onto this piece of work here. This is a model of a building that we didn't work on, actually. This came to us for a peer review. Now, peer review is something that's increased significantly in the UK. Anyone who works and practices in the UK will probably have seen the same thing. Very often, we'll be brought in as a secondary consultant, completely independent, to review another consultant's work, usually by a building control authority, a building control officer, or a fire authority, to review the work and give it a second sign-off. And this is what happened here. So we received a piece of work where somebody had designed a mechanical smoke control system, and they had done that benchmarking against the natural shaft. So they'd said, this is what a natural shaft would do, and this is what a mechanical shaft would do. Ours is better, ergo, safe, we've met our duty. And the way they did that was through doing some CFD modelling using FDS, modelled a natural condition, and modelled a mechanical system iteratively until it was better. But they did something different that we'd never seen before. And I'm going to come back to that after a quick case study. Fast forward a couple of days. Only a couple of days separate these two anecdotes. And we were doing some CFD modelling commercially in my business, not as a peer review, it was our own piece of work, at Admiralty Arch. Is anyone familiar with Admiralty Arch? Yeah? A bunch of us familiar with Admiralty Arch. If you go to London and you come out of Buckingham Palace, as we all do, of course, because we're all Brits, we all go there for tea every day. You come out of Buckingham Palace, you go right down the Mall, it's the big bridge at the other end, the big arch. It used to be the entrance to Buckingham Palace. And it looks like that. It's a former cabinet office where the Admiralty were based. So the Royal Navy were based there. And it's currently undergoing some refurbishment. They're turning it into a top-end hotel and some fancy apartments. So we were engaged to do some CFD modelling on this particular building. And what it is we were modelling is 10 different scenarios. So 10 different cases throughout the building, and we were modelling the firefighting shaft. Now, in this part of London, there are lots of tunnels, and there are lots of secret things going on underground. This is right next to the Cabinet War Rooms, Churchill War Rooms, we've all heard of him. And underneath there is huge basements in this area, 5, 6-storey basements, which for London is quite deep. There's not much going on in London in terms of that depth of development, certainly not these days. And one of the issues we have there for firefighting is how we ventilate those lobbies in the event of fire. It all warrants mechanical systems, so we were modelling each of these shafts. And it resulted in having 10 different scenarios, 2 fires per scenario, so 20 models that looked something like this. So this is an example of one of the basement stories. This is basement level 4. This is the pool and sauna room. Not a lot of fire risk, but nevertheless we had to do some modelling, so we were being paid. And we had to design the mechanical shaft. So what you'll see is that in this particular building, we've got a stair with a shaft next to it. The kind of environment itself that we're modelling, in this case the pool and sauna, and the fire service ingress. So we had these really weird kind of rabbit warren models that we were doing. They're weird scenarios and geometries were all kind of obscure. This is another one. This is basement level 3, the floor above. Again, we're modelling the full fire service ingress, we're modelling the ventilation system and the environment itself. In this case, it's the ballroom. On level 1, we're above ground this time, so we're modelling the whole stair, and we've got this big natural shaft that runs alongside the stair. And then we also modelled the top floor, which is level 4 penthouse. Now, each of these geometries are completely unique. Each one took days to build. We used Pyrosim, but there was a huge amount of complexity in these geometries. And we became quite interested in rationalising this geometry to make our lives a bit easier, because we had 20 models to build of a very, very complex building. One thing you'll note about Admiralty Arch is there's no straight lines. Everything's curved. So it just added another element of complexity for us. So we're really interested in this rationalisation. And 2 days prior to this, as I've already said, I got a report land on my desk from another consultant. And what they had done was rationalise their geometry in a novel way. Now what they'd done is they'd modelled a corridor, like so, with a big long 30-metre shaft, 10-storey shaft next to it with a fan at the top of it, which is exactly as it would be installed. And they presented a case, and this is the crux of my talk really, this idea of a case study. They'd presented a case that said, because it's a completely enclosed shaft made of concrete with a fan at the top, we have a complete mass balance between the top and the bottom of that shaft. There's no leakage paths. So what they'd actually done is they'd modelled that for the sake of the report, and then, and then they ran the models like this. And they put a shaft, they put a vent on the outside of the corridor and modelled directly from there and said, we don't care about the shaft. We're going to rationalise our geometry, reduce it down. We have a mass balance, so it doesn't matter. And we became quite interested in this, because this could save us a huge amount of time on the Admiralty Arch project. So we thought that we can adopt this if it works. So we ran some sensitivities ourselves of this. I don't know if anyone's ever seen this sort of modelling, but it's crept in and it's used occasionally. I see students do it. We became interested in, do we have a mass balance? Is this something that is valid? Do we care? Does it work? So these are some of our models. You'll usually see it's one of my models because it's got a black background. In the Pyrosim results viewer, I always change the background to black so I can tell it's my work, not someone else's. Not to suggest none of the rest of you can. It's not a great invention. It's just you change it to black. But if I'm modelling theirs and theirs is grey, I can tell my work from theirs if I'm doing a peer review. It wasn't supposed to be a big show-off piece, that, but I'll take it. So we modelled here a full extract vent, and we modelled the velocity plot. We were interested in the velocity profile across the aperture, and it looks something like that. We can see that we've got high velocity at the top of the vent aperture and low velocity at the bottom. In actual fact, we get negative velocity profile at the base of the shaft. When you model directly from the corridor geometry, you don't get that profile whatsoever, because of course what happens is your vent gives an even velocity distribution profile at the top of the aperture to it does at the bottom of the aperture. So it completely disproportionately represents how much extract you're getting from that corridor. What it actually does, funnily enough, I laughed at least, it makes the conditions worse, remarkably, because it actually draws your smoke layer down and recirculates it and introduces vortices in there that you wouldn't otherwise have. So, modelling those two side by side again, we were able to prove really, really quickly that actually this isn't a rationalisation. This is a cheat. This is something that somebody's tried to do and they haven't really thought about it and done a quick sensitivity on it. Now, I'm going to have to rattle through quite quickly because I've just missed my timing. We're into the Q&A session. It looks something like this. This is from our work. We've taken this forward to try and solve this and work out, actually, can we come up with a rationalisation from this? You'll see in case one, when you have a full shaft that's modelled, what you end up with is a high velocity profile in approximately the top 20 to 25% of the aperture. Beneath that, you get about 50% of it where you have mid-velocity, and down at the bottom you have low, possibly negative, but negligible velocity is quite common. Whereas if you model directly from an enclosure, directly from the compartment, you get an even velocity distribution, which is not what we expect to happen in a real scenario. Where we've taken this now, we have a next step to this project that we're producing a paper for that will be circulated, but essentially on a project basis, if I can have an extra 30 seconds, I'll get to the conclusion. What we found is that actually you don't have to model the whole geometry. You don't have to do the whole shaft. There is a golden number. We don't know quite what that is yet, but there is a threshold at which point you must model the whole shaft, but it isn't the entire shaft, the full shaft in its entirety. What we found is it's proportionate to the extract volume that you have and the volume of the corridor or the volume of the space that you're ventilating. Not the travel distance, not the length, but the volume. And between those two, you can do a sensitivity and find that you model less of the extract shaft and you do get to rationalise your geometry. On the Admiralty Arch project that we had, we saved between 5 and 7% of simulation time, which doesn't feel like a huge number, but across a large project with 20 models, actually it did save us quite a few days in the end. The way we did that was by doing sensitivity tests of each extract shaft at each extract velocity, worked out the point at which we saw no difference to if we'd modelled the entire, the shaft in its entirety, and we were able to do these sort of reduced, rationalised models and save ourselves quite a bit of time in the process. Now, where we take this next, we are working on a formula for this, myself and my colleague, Renee Goosen. Now, Renee, I think, might be watching this from home. So this is either called the Hart-Goosen formula or the Goosen-Hart formula. All good academics know that that is a constant argument. We have decided, we have negotiated, if it works, it's called the Goosen-Hart. If it doesn't work, it's called the Hart-Goosen. And you will see we're on our third iteration, and it's back to not working. We're currently at Hart-Goosen. If you see it published and Goosen's name is first, it means we've cracked it. What we're trying to do is come up with a formula, a nice little correlation to say, this is how much of the extract shaft you must model based off the extract rate and the volume you're trying to clear. We're having some success. It comes in about 5 meters above, which is a huge rationalization over a 30-meter, 10-story corridor. So, watch this space for the Goosen-Hart or Hart-Goosen formula, and a bit of a case study in there about how we kind of take something for granted if we are reviewing it, and the benefit of doing sensitivity studies, I suppose. And that's me.
Thank you, Joe. Great. Great talk. Questions? Okay. Oh, yeah. I'm going by proximity and not order of hand raise. There you go.
Not that I don't love having fun with FDS and doing what you're doing, but have you ever considered just looking at a simple HVAC, duct model where you've got a kind of a big duct. Your hallway is sort of a big duct leading into a vertical duct, and just looking at airflow and losses through the duct and all that sort of thing. I mean, would that help?
It may do. The problem we tend to have is that we have a vertical shaft built and we've got that sort of dog leg directly next to where we have it. So it's that pressure boundary you get as it turns that corner. Right. So we have to replicate that. So if we're doing that, we might as well model the shaft rather than do something any more complex.
Yeah, and they do have, what do you call them, nodal losses, but exactly what that is in your case, it's hard to say. Okay, thanks.
Yeah, thank you.
That was really interesting. I guess the follow-up question I have is, did you try just making the shaft a coarser resolution, make it a factor 2 coarser, and you'll probably get the same simulation speed up doing that? Curious on the sensitivity.
Yeah, we tend to avoid doing that, only because we don't want to put our mesh interface at a critical part of the geometry, so where we have that extract that's coming, and the reason for that is because that's where we have the AOV that opens. So generally we try to avoid doing that. The mitigation for that is to have the, say, ground floor mesh extend into the base of the geometry and put it there and refine it. Yeah, that does work. I mean, again, we're trying to reduce any of the mesh boundaries from anywhere critical. That's probably the next step that we would do logically. Above that, if we can come up with something that just solves it completely, we'd do that as well. But that, in fairness, is the way that I would personally opt to do it right now, because I don't care too much about what's happening in that shaft. I care about the corridor. That's where I want the more refined mesh. Yeah.
If we can stay on that, great talk. But I'm just to educate me. I mean, you're pulling. You know what the mass loss rate is, right? Aren't you pulling that?
Yeah.
So isn't that the same whether the shaft is there or not? I'm just a little bit confused as to why the recirc pattern matters.
Yeah, I mean, we don't know the mass loss rate. We don't know the volumetric flow that we're going for. That's what we're trying to determine. So if we were to model a natural shaft, we'd say that the corridor clears after 2 minutes, 120 seconds. And then we are modeling different extract velocities until we get that 2 minutes or better.
You have smoke in the corridor and you're watching to see when that clears. And
that's right.
I see.
Yeah. So with the benchmarking against a natural, we're looking for what threshold, what volumetric flow rate do we need as a minimum to get the same as the natural. Yeah. So we may end up doing 10 models until we get it right. Yeah.
Joe, don't suppose you've got a brother called Tom, do you? No, okay.
Do I have no, I don't have a brother called Tom.
No, that's fine.
What's he done?
So, 2 things come to mind. One is NFPA 20, whichever one is fire pumps, NFPA 20, kind of covers this with the way it talks about the turn radius and length of pipe necessary before suction pumps, because of the negative pressure in the water flow. So that has some distance requirements. Might be interesting to look at that and scale it because of the negative pressure component. The other thing is just a comment. You may want to connect with Oliver Knapp at CPP Wind in Colorado. Some of the work that they've been doing with their new wind tunnel might be of interest for this specific item with the way that you've got your negative pressure plane working.
Sure. Okay. I'll get details from you after if that's okay.
Hi, great presentation. Do you think that you could do 2D analysis to do that faster?
Could I do it? Or could Renee Goosen do it? Renee, write that down, you're doing that later. Could you do it in 2D? You probably could. The problem is that if you just fill the corridor with smoke, you might not be representing what would happen in a real fire. So when we're looking at this, we're looking at a shaft and a corridor and a flat. So thinking about it in 3D, we have a certain amount of smoke that's leaving the flat when the door is open for, say, 10 seconds, 20 seconds, 30 seconds. If you could standardize that, I dare say you could do a 2D model only, just of the corridor and shaft. And in actual fact, that would work nice as a comparative, because you could do natural versus mechanical, keep the smoke volume the same. I dare say you could, yeah.
There's a comment online. Can you watch out for the turbulence of the smoke in the shaft and sort of see that once it's constant, any point after that will be the same and fairly unidirectional?
That's exactly where we're coming up with our correlation from. It's the point at which that's uniform that you know is the height that you are not too concerned, because you could put a solid vent there and it'd give you the same. So yes, in fact, that's what we'll look.
Yeah, he says he means by checking something like the Reynolds number. It's
yeah,
something like that.
Exactly right. Yeah.
Okay, and then just make sure here, nothing in chat. Things are splitting a little bit here between chat and Q&A. All right, good. Okay, let's go here and then here.
Hi, congratulations for the presentation. Often in other software, in other CFD software, they use what they call the hydraulic diameter of the shaft, which may be considered a diagonal dimension of the shaft. To correlate the length, you have to extend the shaft. Did you do some sensitivity analysis by varying the sectional area of the shaft and consequently the hydraulic diameter to understand what's the link between the hydraulic diameter and the length you have to actually place?
Sorry, no, yeah. No, we haven't. The reason that we haven't is because it's a standardized mechanical shaft that we would have if we were designing into a building. We've got a 0.8 meter squared and we have minimum and maximum values for that. It is something that I would add to it, because I think that actually it'd be, should we solve this and we get ourselves our Hart-Goosen / Hart formula, we'd be able to play about and come up with a better standard or a better kind of exemplar geometry that we'd use. So no, we haven't, because we've just got a standard that we're using, but it is an interesting thought to be able to do it. I'd like to model a square shaft as opposed to a rectangular shaft, because I think that exacerbates this velocity profile. It pinches, literally is the pinching effect that you have, whereas actually our standards say we ought to use a rectangular shaft. But I think a square shaft would be safer. Did it? Oh, well, let's have a case of beer tonight and undo it. Fix it. Quite right too. Yeah. Richard.
Question. So that velocity profile that you were seeing and that kind of dog leg of the shaft, what did you see, or was there something different that you saw if your entrance into the shaft was kind of midway through, per se, kind of halfway up the building, if you will?
What do you mean? Sorry.
So not kind of located at the bottom of the shaft, or is that how it's all designed? So is it one continuous shaft down the building, and say if you had a flat on the fourth floor, it would kind of be in the middle of that? So what kind of velocity profiles were you seeing in that?
I see what you mean. The velocity profile, the higher the velocity, the more it overcomes that negative influence you have from the floors below. So what I mean by that is if you have a straw and you kind of bite a hole in it and you've got the bit that's below, if you have a low velocity, you have an impact there because you're creating turbulence below. The higher the velocity, the more it overcomes that fact. Now, what we don't have at the moment in these shafts is a kind of damper that closes off and you only vent from the floors above. You do have the sections below that are also there. I found that higher velocity overcomes that. I find generally when people model this, they don't model the bits below. It is a problem. Of course, in our basement vents, we had to, because we were modeling the whole shaft top to bottom. I actually think it introduces a huge error percentage when people don't, because they cap the bottom of the shaft as though there is a physical obstruction there. You'd be safer to put an open mesh boundary or something like that. But I rarely see people, as good practice, modeling the true geometry right the way down to ground floor or basement or something like that. But yeah, higher velocity is the one that overcomes it. It's a risk when you've got low velocities. 4 meters cubed per second, something like that as a threshold, you are introducing turbulence that is a risk. Yeah, recirculating smoke down the building. Yeah.
Okay, with that, I think that'll be it. Thanks, Joe.
All good. Thank you.